All right, we just learned about what a first derivative tells us about a graph. Surely there's something that the second derivative tells us. So let's just look for a second at these four graphs up here. You should be able to look at them and tell me where is the derivative positive or negative. That should be pretty fast. So in this first one, it's increasing everywhere, so it is positive everywhere. And this is decreasing everywhere, so it's negative everywhere. And then these two change, right? They go from a negative value to a 0 to a positive value. And a positive value is increasing to a 0 to a negative value. Notice we're always going from left to right. However, if we think about this a little bit more, it looks like it's positive to the left, but just barely. And then it starts getting steeper, and as it gets steeper, that derivative increases. So my derivative function starts close to 0 but positive, and is getting higher. In fact, maybe it's even asymptotic here. Maybe it's even curling up. Okay. So if this is my x-axis, it's always positive, but as I go to the right, as my original function gets steeper, my derivative function needs to go up. And it looks like it's kind of approaching 0 but never getting there, so maybe this is also asymptotic. All right, so what about this second one? It looks like it is decreasing, so it should be negative the whole way through, but it's getting more and more negative, so it's getting steeper and steeper down. Okay. Similarly for this one, it looks like the derivative is 0 right about here, but it starts positive and then it goes negative. So my derivative might actually look something like this. Right? It starts off above the x-axis and then gets negative. And the opposite for this last one. So my derivative function might be a 0, I don't know, right about here. But it starts negative, really negative, and it gets flatter and flatter and flatter, and then it gets more and more positive. So that's my derivative function, but you'll notice that if the derivative function is changing, if that value is changing, then that says something about the second derivative. Right? If there is a change in a function, then its derivative is going to be positive or negative to reflect that. So this first increasing derivative is telling you something about that it's getting steeper and steeper because my derivative is increasing. This is telling you that my slope is getting more and more negative because my derivative is decreasing. And similarly with the last two. So the second derivative is telling us the change in the first derivative. It's kind of like asking, the first derivative might be asking for a velocity, and my second derivative might be asking for an acceleration. So what does this say about a graph? Well, something about the curvature. Something about this curvature is making that second derivative be positive or negative. It's making that first derivative change. All right, a lot of words. Let's go ahead and define something here. I want to talk about curvature. I need an official way to talk about it. So here's my definition. F is concave up if the graph lies above its tangent line, at least at a point. So if I go back up to this example here, this third example is concave up because its tangent line is always beneath it. Right? It is curving up away from its tangent line. That's telling you that the first derivative is increasing. Okay. F is concave down if the graph lies below its tangent line. And so this fourth one is a nice example of that as well. Okay, the graph is always below its tangent line. It's sort of curving away from it. That means that the first derivative must be decreasing. So just to go through this first one is concave up. It's kind of curving up. This is curving down, so it's concave down. Curving up is concave up, and then curving down is concave down. 4 quick examples of concavity. Good vocab word for you. And the second derivative is really telling you about the concavity. Is it curving up or curving down? So hopefully you can figure out this by now. We've got something called the concavity test. F double prime, the second derivative is bigger than 0. That tells you it is concave, well, up. And if f double prime is less than 0, if the second derivative is negative, then it is concave down. Great. So we should be able to tell this in both directions. If I know the second derivative, I can tell you something about the concavity. If I can see the graph, I can tell you something about the second derivative. So let's go ahead and use our example from before. We had a first derivative of 1 minus 2 sine x, and a second derivative of, oh, I guess we haven't done that yet. Let's do it. The derivative of 1 is a 0. So we get a negative 2 times the derivative of sine, whether you know it or not, is just cosine. That's nice. Great. So let's go ahead and graph these just to make sure that this kind of makes sense. I'm going to graph x equals to, I'm going to go ahead and graph minus 2 cosine of x over here on the right. So cosine starts at 1, but we're going to go ahead and start at negative 2 because we're taking negative 2 times that. Cosine becomes 0 at pi over 2. Okay, and just maybe a quick reminder on the unit circle. Here's 0. Cosine is the x value. Here's pi over 2. Cosine is still the x value, so we're at 0. And then here is pi. So now at pi, we should get a negative 1, except we're multiplying that negative 1 by the negative 2 out front. So we're going to get a 2. And then right back down to 3 pi over 2. Okay, and it's this nice periodic wave, right? So we could even continue this pretty darn fast. Okay. So if I connect these dots best I can, something like that. Yep, this nice wave. So this is my second derivative. Okay, and what this is telling you then is that where this is negative, we are concave down. Where it's positive, we are concave up. So concave down from negative pi over 2 to pi over 2. Okay. And concave up from, looks like pi over 2 to 3 pi over 2. Okay, I'm going to cheat a little bit here. I'd like to graph the original function, but I'm going to go ahead and ignore that x. Let's just look at the 2 cosine of x part of it. Okay, so I'm just going to focus on this part right here. So that's really going to be what's contributing to our concavity in this case. Go ahead and graph the whole thing on a calculator if you want, but this will be easier for me to graph if I just focus on the 2 cosine of x. So if I just focus on the 2 cosine of x, I'm going to start up at 1. It's also going to go down to 0. And 0, and then I'm going to go down to negative 2 at pi, and then right back up to 3. I just realized that my scale is off on the top one. It really should be about here, right? All right, you'll forgive me. Clean that up. Deep. Okay, so again, that scale right on the second one then is going to be right about here, and I'll do my best to connect these dots for you. Something like that. This one goes away. And that's my nice cosine wave, just kind of times 2. So it affects the amplitude. And what do we see here? That where's my concavity down? What am I curving down? Well, it looks like I'm curving in a downward direction right here. And then I'm curving in an upward direction all throughout here. And if I kept going, you'd see it kind of curves down in this area and it curves up in this area. And so that curvature, that concavity rather, is periodic, just like my original function is periodic. So when this is concave down, we have a negative second derivative in here. And when it's, when this is concave up right here, no, there we go. When this is concave down, we have a negative second derivative. When this is concave up, we have a positive second derivative. All right, so it's nice to see that they're talking both in graphs and in algebra. Very neat. So what about when it's changing? What about those magic points when it's switching from a positive to a negative concavity? So for instance, this magic point kind of right here, or this magic point right here, or right here, when that concavity is switching. Well, those actually are pretty important in a lot of fields, and so we have a name for them. They are called inflection points, and that's just a point on a graph where the concavity changes directions from up to down or down to up. So here is that last graph, or rather that last function with its second derivative. We want to know where it changes. Well, then I'm asking myself, where does the second derivative of x equal 0? And that's just where 2 cosine of x equals 0. That I hope you do know on this domain. In fact, you've already used it a couple of times. It looks like that is going to be on negative pi over 2 and at pi over 2 and at 3 pi over 2. Okay. On the domain that was given above, we're going from negative pi over 2 to 3 pi over 2, so I could draw that number line again. And I could play this game where I say, actually the very end of it is negative pi over 2. And the other side of it was 3 pi over 2. And then I had this pi over 2 in the middle. Okay, and we said, oh yeah, these are the zeros. What's happening to cosine? Well, cosine is going from a positive value, because it's positive at 0, to a negative value. Okay, so my second derivative is changing from a plus to a minus, which means that I have an inflection point so I get pi over 2, plug that in to my original function, so pi over 2 plus 2 times cosine of pi over 2. Do you know what that is? Well, that's a 0. We already decided this. Okay, so I can actually erase that whole part there. So just at pi over 2, pi over 2. Very neat. All right, more next time.